Previously, we discussed how to use a one-way ANOVA to examine if the means for 3 or more populations are all the same, or whether at least one population has a mean that's different from at least one of the others. Because we have more than 2 groups, we can't just look at one mean minus another mean like we did with the z-test or t-test. We have to look at the differences between 3 or more groups all at the same time. Now, our last video left off noting that we do that by calculating a new test statistic, the F-statistic, which measures the variance or variability that we see between our groups relative to the variance or variability that we see within our groups. So let's take a closer look at the F-statistic, starting at the conceptual level and why it works. Now, mathematically, the F-statistic is equal to the variance between groups divided by the variance within groups. We'll address exactly how to calculate these two variances later, but for now, let's not worry about that. We can abbreviate these as the s squared between divided by the s squared within. Notice we're using a lowercase s squared because we'll estimate these variances based on our sample. Now, to understand why this works, let's spend a little time exploring what these two parts of f, the numerator and the denominator, are telling us. Let's see exactly what it is that they are in fact estimating. We'll start with the denominator, the variance within groups. Now, for conciseness, we'll typically just call this the variance within. But whether you call it the variance within groups or the within groups variance or the variance within, it's the same thing. Now, to see what it estimates, let's say that I have these 3 populations, red, blue, and yellow. What's the variance within each of the populations? And let me emphasize at the moment, I'm talking about the population variance for each of these populations, their sigma squared. Now, you might think that it's just 3 different sigma squareds, right? A sigma squared for the red population, a sigma squared for the blue population, and a sigma squared for the yellow population. But remember, one of the assumptions for a one-way ANOVA is that the variances of the different populations are all equal. They're all the same sigma squared. All 3 sigma squares have the same value, that common population variance, sigma squared. So when we sample from each of the populations, the variance for each of those samples, s squared, our lowercase s squared, is an estimate of the same sigma squared value, right? They're all estimating the same sigma squared. The variance for the red sample, s squared for the red sample, is estimating sigma squared. The variance for the blue sample, s squared for the blue sample, is also estimating the exact same sigma squared. And of course, the variance for the yellow sample, s squared for the yellow sample, is also estimating the exact same sigma squared. Now, of course, each sample will have a slightly different estimate for sigma squared, but because they're all estimating the same value, we can pool them together to get a single better estimate of sigma squared. And that's what our variance within is estimating. It's estimating the true population variance in our populations. Now, students sometimes ask, why do we need assumptions like equal variances? That's why. Now, if the variances aren't equal or you're not comfortable assuming that they're equal, there are things you can do. But that's for another class and a different video. So, the variance within estimates sigma squared. Depending on the textbook, you may see this written as the expected value of the variance within, E with in parentheses S squared within is equal to sigma squared, because, well, that's what we expect it to be, even though we know it'll be a little different due to random variation. It won't be exactly equal to sigma squared. Or you might see that same point expressed as the variance within is approximately equal to sigma squared. They're just ways of saying that it's an estimate of that population variance. All right? So that's the variance within. What about the variance between groups, which we'll call the variance between for convenience? In a simple one-way ANOVA, the variance between groups estimates two things added together. Like the variance within, it also estimates sigma squared. But, and this is important, it also adds in an estimate of any group differences or group effects that may exist between the populations. Mathematically, you may see the variance between described as the expected value of the variance between, E and then in parentheses S squared between, is equal to sigma squared plus group effects. Or you may see it described mathematically as being approximately equal to sigma squared plus group effects. Now, also, I should note that you may see people use the term treatment effects instead of group effects. The phrase treatment effects just harkens back to classical experimental designs where you assign participants into different experimental conditions. But in this context, in this case, group effects, treatment effects are the same thing. Now, you might look at that and think, what the heck do you do with this sigma squared plus group effects thing? I mean, let's face it, it does make F a little more complicated and more than a little less intuitive than a Z or a T. But, as we'll see in a moment, at a conceptual level, it's still basically the same idea of what effect did we see relative to what would we expect to see if the null is true. To understand that, let's look at how the variance between works in a couple of different situations. First, let's start with a distribution of three different populations. What would these populations look like if the null hypothesis were true? All right? Well, if the null hypothesis is that the means of the different populations are all equal, then if the null is true, these populations would look something like this. No difference in the means, no group differences. And remember, we assume that the variances for each population is the same, sigma squared, so the populations would perfectly overlap. So what do we end up with then? One big distribution with a variance of sigma squared. There's no additional variability. The only variability is sigma squared. There are no group effects. Group effects equals 0 because the means are all the same value. So what does that do to the variance between and our value for our F statistic? Remember, F is based on our estimate of the variance between, S squared between, divided by our estimate of the variance within, S squared within. And we previously noted that the variance within estimates sigma squared, and the variance between estimates sigma squared plus any group effects. So F is estimating sigma squared plus any group effects divided by sigma squared. But as we just saw, if the null is true, there are no group effects. Group effects equals 0. F then just reduces to sigma squared over sigma squared, which is equal to 1. If the null hypothesis is true, we expect to see values of F somewhere around 1. Now, on the other hand, what if the null is not true? Okay? If the null hypothesis is not true, then the means for the different populations are not all exactly the same. In that case, the distributions would look more like this. They don't completely overlap. There are differences between our group means. Now, as we noted, the variance between is still estimating sigma squared, but it's also estimating the group effect. Now, in this case, it's no longer equal to 0. And the bigger the differences between means, the larger the group effect will be. So what does that do to our variance between and the value of our F statistic? Well, you can see that the larger the group effect, the larger the variance between. And given the variance between is in the numerator of our F statistic, the larger the variance between, the larger the F statistic. So with no group differences, we expect F to be equal to 1. But as the group differences increase, F gets larger and larger than 1. Visually, it looks like this. The larger the difference between the group means, the bigger and bigger and bigger F will become, because the group effect in the numerator will get larger and larger and larger. All right? Now, of course, just like any statistical test, even if the null is true, we don't expect the sample means to be exactly equal because there will be random sampling variability. Consequently, even if the null is true, we shouldn't be surprised if F is a little different than 1. But just like other statistical tests, the more extreme the F, the less likely it is that the null is true. The less likely it is that the population means are all equal. So, just like with T's and Z's, the question comes down to whether the F is so large that we're comfortable rejecting the null. Is the effect so large that we're comfortable concluding that the group effect in our sample is just too big to be random error, and we should reject the null and conclude that the population means are not all equal? Now, a couple of things to recognize and remember as you're doing a one-way ANOVA. First, remember that both the variance within and the variance between sigma squared in both of these is being estimated. So even if there is no group effect, the S squared within and the S squared between will almost certainly be different values, even though they're both estimating that same sigma squared. And because of that, you can get F's that are less than 1. You can think of that as indicating that you're seeing even less random variation between the samples than you would have expected. And Also, if you think about it, you may recognize that f is never a negative number. It always ranges from 0 to positive infinity. Do you see why? It's because both the numerator and denominator are based on squared values. Variances are squared values. They're the sum of squares divided by the corresponding degrees of freedom. Because they're squared values, they have to be positive, and thus f can only be positive. It can't be negative. If you ever calculate a negative f, you know you've made a mistake somewhere. So, unlike the z or t tests that range from negative infinity to positive infinity and can be two-tailed, the f-test only ranges from 0 up to positive infinity and is always a one-tailed test. So that simplifies things a bit when you're doing a one-way ANOVA by hand. Now, with that, let's wrap up this video. So far, we've talked about the variance within and the variance between at a fairly abstract level and haven't discussed how they're actually calculated. We'll learn exactly how to do that in our next video. Bye-bye.